All right, so I'm going to go ahead and go through the quiz that you guys just took, or test you just took, and so that way you guys can learn from this. I'm also going to have a different version of this quiz with different questions that I gave elsewhere, and I will post that as well for you. So you should look at both the quiz you took and the other one that I'll post on the big plan. In any case, this is what you guys just did. The first thing is it was a little annoying because they didn't give you the index of refraction, but since they gave you the angle on both sides, you could cross multiply from the equation booklet and you can come up with this equation and solve for the velocity. You would have to recognize that out here where you have sine 46, you have the velocity of 3 times 10 to the 8th. So this is nicely done. We have this side is the ones. This side is labeled twos, excuse me, velocity 2, theta 2, n2, lambda 2 are all on this side. And then in the ice cube, we have v1, theta 1, lambda 1. Everything in here is the ones. And then just carefully use the equations, set them up, and 3 times 10 to the 8th will go smaller. There's a couple of you that end up getting bigger, but just remember light can't go faster than this. So if you get a bigger number, then maybe you mixed up the ones and twos, which was a pretty common mistake. For the wavelengths, we know that it's speeding up. It's going to get to a smaller angle, so it's going to be a smaller wavelength. So we expect a wavelength less than the 550. So there are a couple of you decided to get like 700 or something if you had this flipped upside down. But we know that the wavelength has to be smaller when the angle is smaller. So in the ice cube, we should get about 420 nanometers. Index of refraction, you could get that from any of these ratios because it's just the ratio. Looks like she chose to do it with the sine ratio, but it ends up being 1.3. And some of you had the index of refraction being less than 1, but remember, it can't be less than 1. Index of refraction, always greater than 1 for light. Okay, for light, it can always has to be greater than 1. Since in a vacuum, it's just going as fast as it can ever go out here. Okay, let's see, where are we at? Next, we have the critical angle question. So we put in 90 degrees out here, because here it comes up and it hits the side AB. And as it's exiting, we put 90 degrees. We go ahead and we solve for that. And we find that we have a angle in there of about 49 degrees for the critical angle. And since this angle is 33 here, that's going to be 57 there. Remember, this is a right triangle, and you got to do a little bit of geometry there. So this ends up being 57, which is too big. So that's unfortunate. That means it has to totally internally reflect. So there's lots of ways to explain that. There was a lot of marks associated with this, so make sure you're also doing a good job of explaining it. For some of you, you tried to use the fact that the arc sign gives you an error, which is fine. That's a good argument. But you need to keep on with the argument to say that the only reason that would happen is because there's total internal reflection, because the outgoing angle can't be bigger than 90. Make sure you actually explain it. Instead, I think probably the better way to attack it is to actually calculate the critical angle, and then you can just say that this angle is bigger than that because 57 is bigger than 49. So that's a good way to do that. For E, it asks, well, what happens after this total internal reflection? What happens here? And it isn't shown here, which is unfortunate, but it's explained nicely down below. But in any case, since this comes in at 33 degrees from the perpendicular, so here it comes in, we have 33 degrees here, and it comes in, so it's going to come out, and if you do the math, you'll end up getting 46 degrees again, or you can just look at the symmetry of it. If you have 46 comes in to be 33, then if you have 33 on the inside, it's going to come out and be 46 on the outside. But it'll refract and come on out over to here. A lot of you thought for some reason it would totally internally reflect, but that's not true because it's 33 degrees. We'll get some reflection and we'll get some refraction, but they really wanted you to talk about the refraction as it leaves being 46 degrees as it exits there. So this is nicely explained here, but only if you have a picture to go with it, which she does. Okay, we have minimums happen. This is this new question where we've switched over to the double slit, and we're using the double slit equation, as you can see here. And when we solve this for lambda, we make sure everything's in meters. And since everything's here in meters, we end up getting a lambda that's at 3.2 centimeters. So nicely done for part 2. For part 1, you had to say destructive interference, but you also had to mention that it was out of phase. There was a pi phase shift or 180-degree phase shift between the two waves that are coming in. The next part's on polarization. They switch over to these different waves, these microwaves from the antennas. And so, or radio waves, I guess it was, doesn't really matter because we're just looking at the polarization. And since the transmitter creates polarized light, then the antenna must be parallel, so it has the same plane of polarization to receive all of the information. And so you need to mention polarizing, you need to mention that the receiving antenna, in order to receive that polarized light, needs to have the same polarization angle. A lot of you understood to use cosine squared, and so you did, cosine squared of 30. So you do cosine of 30, you take whatever that number is, and then you square it. And then you're going to take 12 divided by that number, and don't forget to put the microwatts here. Finally, the easiest question on the whole quiz was just to get the velocity is distance over time. So take velocity equals distance over time, solve that for t, and you get about 1.9 times 10 to the negative 4 seconds. So that's your quiz today, and look it over, maybe do it again from scratch and make sure you're good at it. Have a good spring break.